Hey friends, welcome back on my channel. And today I'm going to have with you some kind of a conversation about Heisenberg uncertainty principle and the Fourier transform in quantum mechanics. So, if you're interested in finding out what is a Heisenberg uncertainty principle as a foundation of quantum mechanics and what are the hell Fourier transforms, then please continue watching the video and let's come along. So, I'm going to have some kind of notes next to me to explain you. They are going to be showed next to me here as well. So, what is a Heisenberg uncertainty principle? Probably you've heard about it already. It's some kind of a thing or principle that, how would I say, forces you or restricts you of knowing everything about particles. You cannot know both parameters in case they are written in Heisenberg uncertainty principle. For example, position and momentum. You cannot know simultaneously the position of a particle and a momentum of a particle. It's restricted by the principle. However, probably you know the notation already. Delta P times delta X equals or more than H bar. It basically tells us so we are not able to know it more precisely rather than this H bar parameter. It actually equals to usual 1h or Planck's constant over 2 pi. So, but what it tells us, what's significance and where is the principle actually coming from? Why don't we say so? Physicists just came up with such a principle, so because of they're not able to understand the nature and explain it fully, because of it they made up the principle. What a shame, physicists. However, it's a real principle that works. So let's try to explain it. For example, we have a football, for example, and how are we measuring its, for example, momentum? Momentum is m times v, so it's mass times velocity. In case we know velocity, we some kind of measure momentum. So, how do we know the velocity of some kind of football? Well, we look at it and comparing with environment, with environmental conditions, we're able to find out what is the velocity of the football. We actually know, in this case we know both and momentum and position. Is it really possible? Because of the Heisenberg uncertainty principle should not allow it for us. However, we are still able to do it. What's happening? The real world or classical physics is happening here. So, because of the football is enormously big, how are we measuring it? We are measuring it by our eyes. We look at it. Some kind of light is coming to our eyes, then it reflects to the ball, or light basically strikes the ball and reflects to us. And our brain some kind of constructs a picture. So there is some light which was reflected by the ball. Oh, it's a ball here, and we are able to understand where it is. Well, I would say the light, light is some kind of a particle, or it's created by a stream of particles, photons. You know about them pretty well. They kind of have some mass. They are carrying it, or either way they would not have any energy, from a formula mc squared, as you know. So the photon is kind of bouncing on the ball, and it's kind of changing its velocity when we are looking at it. It strikes by a little bit, but how would I say, but the change is so infinitesimal, so it's absolutely small. It's kind of, we are just not counting it in our classical physics, because nothing is going to change of plus 0.0000000, endlessly many zeros, and then 1 meters per second. So nothing is going to change because of it. We are just forgetting about the concept, and by this way we are avoiding Heisenberg uncertainty principle. But in case we have an atom, atoms are small. They are much smaller than a football. So in case the same photon strike an atom, well, what do you think is going to happen to an atom? It's just like two balls, those have some kind of a similar mass and velocity. In case one strike the other, what's going to happen? Just like, look at my hands. It's kind of reflecting the energy, going to the other one side, even according to the, according even to the classical physics we know, so something is going to happen. Momentums are kind of compounding. So we are going to change its, how would I say, momentum. But what's happened to the photon? Look at it. It reflects back to us. See? And it has some kind of remembering where is the concept, where is the object, an atom. It transports to us position, and we know the position now. We are able to know the position, but the momentum is no more accessible to us. We don't know what's it. We know the position, but we don't know the momentum. Brilliant. It's Heisenberg uncertainty principle. When I explained it all to you, let's look at some kind of how would I say, proof, a nature proof or real proof that is able to be shown on quantum mechanical level. Let's look at hydrogen, or you're able to look at your periodic table, and the first element which you are going to see is going to be hydrogen, and a hydrogen atom. So what do we know about its energy levels in terms of electrons? So, well, the electron of hydrogen atom is located at the first level, or 1s1 level, or it also known as it's also known as a ground state level. Ground state. Well, ground state level. Nothing is able to be smaller than that. Electron is grounded. It has the lowest energy. So, and what do we know about it? It's spinning here. Yep. Is it really? Let's think. Does it have an angular momentum? Well, in case you know the letter, this one letter, it's angular momentum, angular. You see that it actually equals to 0. And if it actually equals to 0, then it should not move around, because there is no momentum here. Nothing is forcing it to move by an orbital. Well, if there is no such motion, what's going here? In this concept, it has still some momentum, a momentum that is not angular, but rather the straightly pointed momentum. So, and because of the momentum, it's still moving. So, but how is it moving? Look at the picture. It has to go through the nucleus of the how would I say, of the hydrogen. And, well, what's in the nucleus of a hydrogen? Proton? Yep. Proton, and in case an electron falls on a proton, what's going to happen? Well, you're right. We're going to have a neutron. It means all of the hydrogen atoms basically have to be neutrons. 75% of our universe are neutrons. Is it possible? Well, not. It's impossible. In this case, most of the processes are going to stop, and we have a great deal of free neutrons, which are going to bombard us. The life is not possible in such conditions. So, what's then happening? Well, the other one concept is happening. And the name of it, well, the Heisenberg uncertainty principle. You're able to ask, is it really the angular momentum equals to zero? But I would say yes, it actually equals to it. I'm not going to prove, but you're able to find some kind of the formula in Wikipedia. It's not a total angular momentum, but well, it's an angular momentum that we know accordingly, how would I say, magnetic quantum numbers. Actually, in case we put in the formula L equals to 0, because of the first energy level has a magnetic momentum equals to 0, well, it basically has to equal to 0, the L squared, and L itself as well has to equal to 0. And it's true. But in case we put it in Heisenberg uncertainty principle, look, it's our L, and it's our inequality basically. But if it equals to 0, when we multiply it times position, well, we are going to have 0, not an H bar. And it means, so the concept, some kind of, how would I say, the momentum here is not actually 0. There is some kind of momentum that is not, which is kind of repelling electron from the proton, and remember, so there is how would I say, there is some kind of potential that attracts electron to the proton, and so it has to overcome the force as well. Because of it, actually, the energy was created, the ground state energy. Because of it, it is. So, if I'm not mistaken, it's a meg times h bar over 2. Something the same, yep. And, well, it's a proof that Heisenberg uncertainty principle is real, because otherwise all of the universe would crash and nothing would be formed. So, but what about Fourier transforms? Fourier transforms are, I would say, modifications of Heisenberg uncertainty principle. they are quite good to work with. In case with Heisenberg uncertainty principle, we were working with position and momentum themselves. Sorry. But in Fourier transforms, we are going to work with probabilities, or better to say, wave functions of position and momentum, like you see here. So knowing the how would I say, the position wave function, you're going to know the the momentum wave function as well. So it's absolutely great tool to use in case you work with quantum mechanics. So you'll be able to know probabilities as well. You're able to count the probability of, for example, position, and then knowing the wave function of position, you're going to kind of take a square root of your probability. You're going to find out what's a probability of finding a real momentum, finding a real, again, momentum. Is it really possible? So in case your probability is 100% to find a definite position, well, the probability to find a definite momentum is going to be, guess what? Of course, 0, because it again is connected to Heisenberg uncertainty principle. Well, in case you want to know the formulas of Fourier transforms, you are able to see them here. That's a Fourier transform of momentum, and this is a Fourier transform of position. The concept is named as side twiddle of P. Twiddle sign is actually connected to Fourier transform. So, as you may guess, actually. So, and what's actually it equals to? It's just an integral of, how would I say, position wave function with e to the power of minus I px. The concept is quite standard because of it's an eigenfunction of all position of all states of such how would I say, atom or particle. So and in case we look at oh sorry, I forgot to twiddle. So in case we look at position wave function, well, we are going to discover just the same structure except for the plus sign. In case you noticed it, here is a plus, here is a minus. So because of it, actually, position and momentum in Fourier transforms are they are named as Fourier conjugates of one another. And the same concept is happening with energy and time. It's all what I wanted to say you. I was glad so you listened to the concept. And if you liked the video, please smash the like button and subscribe on my channel. And I'm going to create and share even more videos about quantum mechanics. So, in case you have some kind of comments, then please comment down below, and I'm going to see you in the next videos. See you soon.